This lesson is on the second half of lesson 7.3 on rational exponents. So now that we kind of know how to switch back and forth to different forms of the exponents and the radicals, we're going to kind of put it all together and help us use it to solve some equations involving those exponents. So this first part in your notes just kind of gives us a couple of strategies or steps we might take in a particular problem. So similar to solving an equation, we want to try to get the x all by itself, but the x is often going to be our exponent, so we got to work on how do I balance those two things out on both sides of our equation. So one step we might do is we might need to isolate the exponent part, which is just like solving a regular equation. So in this case, we have 4 to some x power minus 2 is 14. So we want to get the 4 to the x by itself. So we're going to add 2 to both sides, and we would get 4 to the x is equal to 16. So that may be one of the steps we take. Another step we might do is we want to make sure that the bases are both the same. Right now I have 2 as a base and 16 as a base, and right now it's to the first power. But I want to rewrite it so it has the same base so I can focus only on the exponents. So we do that by looking at that smaller base 2, and we look at, can 16 be written as 2 to some power? Well, 16 is really 2 to the 4th power, so I can rewrite this equation as 2 to the x power is equal to 2 to the 4th power. So we wrote them with the same base. All right. Sometimes when we're dealing with a fraction, we might have to think about how do negative exponents come into this. So again, we're going to try to rewrite this side to have the same base. Well, 9 is really 3 to the 2nd power. So I get 3 to the 2nd power, but it's in my denominator. My other side of the equation is 3 to the x. It's in the numerator. So I need to bring that 3 to the 2nd power up out of the denominator. Remember that when we cross over that line, it switches the sign in our denominator. So instead of 1 over 3 to the 2nd power, that's really the same thing as 3 to the negative 2 power. And then our last step is, once the bases are equal, which is kind of what we've done in the last couple examples, we can drop the bases and just set the exponents equal to each other. So here, 5 to the x power is equal to 5 to the negative 3rd power. So we basically drop the bases, and we say that the exponents have to be equal, so x is equal to negative 3. All right, so let's see that in action. So for these first couple, is just 2 to some power, and we already know what it's got to be equal to. So we're going to take kind of that step 2 of how do I rewrite this number as 2 to some power? Because I want it to be equal to 2 to our x power. Well, 128 is 2 to the 7th power. Okay? And if you're not sure, this is where your calculator comes in. You can try 2 to the 5th, 2 to the 6th, 2 to the 7th, until you find the number that we're looking for. Here, the bases are the same, so now we can drop the bases, and we're just left with x is equal to 7. All right, same thing here. We've got 2 to the x, but we want to change 512 into 2 to the same, or we want that same base of 2, but now we got to figure out what exponent goes with it. Well, 128 was 7, so times 2 would be 256, that's 8. Times 2 would be 512, that's 2 to the 9th. So x is equal to 9. Here, we're going to have to do a little bit of both. So we know we have a base of 3, so let's rewrite 27 out of as a 3 to some power. That's going to give me 3 to the 3rd power, but it's in the denominator, so in order to move it up out of the denominator to the numerator, it's going to switch to a negative 3. So 3 to the x power is equal to 3 to the negative 3rd power, so x is equal to negative 3. Basically, we get it to where we can ignore the bases and simply look at our exponents. All right, so let's start to see that in some larger problems. So here, I already have the same base, so that means the exponents have to be equal to each other. So 5x plus 4 has to be equal to 29. So I do some quick solving. This part should be easy because it's just solving two-step equations, and I get x is equal to 5, which makes sense. If I were to plug it back in for x, 5 times 5 is 25, plus 4 is 29. All right, next one's a little bit more complicated, but we have the same bases, so we can focus solely on the exponents. So we have 4 to the x minus 1st power is equal to 2 times x plus 3 minus 4x. So we've got some distributive property, some combining like terms. So I get 4x minus 4 is equal to 2x plus 6 minus 4x. Combine those like terms, and I get negative 2x plus 6. Now I'm going to add 4 to both sides to get rid of that subtracting 4. I'm going to add 2x to both sides to get rid of my x. So I'm kind of moving those two pieces over. And I get 6x is equal to 10, divide by 6, and x is equal to 10/6 or 5/3. Okay? So it's perfectly okay to get a fraction for one of these. It's all a matter of how the math works out as long as you solved your equation correctly. All right, so next one. I've got a base of 3, so my first step is I'm going to rewrite the other side to have the same base of 3. So 3s we're not quite as familiar with. Okay, but you can try some different things, and we find out that 3 to the 5th power is the same as 243. So we're basically just swapping out what it's equal to. My bases are the same, so I can focus on my exponents. X minus 3 is equal to 5. Quick one-step equation, and x is equal to 8. Okay. All right, now a little bigger problems. Some of these are going to require just a little bit more work with them. For this one here, my bases are the same, so I know my exponents have to be equal. So I get negative 3x is equal to 4x minus 3. I'm going to move my x's over to the left-hand side, so I get negative 7x is equal to negative 3. Divide by my negative 7, and x is equal to 3/7. All right, next one. So I've got a base of 4, so let's rewrite 64 to be out of an exponent of, or to have a base of 4 to some power. So I get 4 to x minus 3. 64 is really 4 to the 3rd power, 4 times 4 times 4, which is otherwise known as 4 to the negative 3rd power when I move it up out of that denominator. All right, so my bases are the same, so I can kind of ignore those and focus on making sure my exponents are equal. X minus 3 is equal to negative 3. So I'm going to add 3 to both sides, and I get x is equal to 0, which feels weird, but remember, we want to plug it back in here. We said 1 over 64 is really x, or is really 4 to the negative 3rd. Well, 0 minus 3 is 4 to the negative 3rd. So it really does equal the same thing. All right. Next one, 2 to the 4x plus 3 power is equal to 2048. So we know our base is 2. So let's rewrite 2048 as 2 to the some power. So we know 2 to the 9th was 512. So 2 to the 10th is 1024. 2 to the 11th is 2048. So we just try a couple until we find one that works. Now I set my exponents equal. 4x plus 3 is equal to 11. I get 4x is equal to 8. Divide by 4. And I get an x is equal to 2. Which makes sense. If I plugged in 2, I would do 4 times 2 is 8. Plus 3 is 11. And that's what I wanted to get, 2 to the 11th power. All right. Hopefully these are starting to make some sense for us. Give these a try if you think you're up for it, or otherwise go along with me. So I have a basis of 9 and 27. Okay? So 9 to the 2nd power is 81, so there's no way to make a 9 into a 27. So instead of a base of 9, what if we made these a base of 3? So 9 is really 3 to the 2nd power, and then I have to the power of 4x plus 3. 27 is really 3 to the 3rd power times x minus 2. Okay? So I've got my same bases, but I've got a power raised to a power. So remember our exponent rules. A power raised to a power just means multiply those exponents. So 2 times 4x plus 3. Same thing here. I'm going to multiply those exponents. So 3 times x minus 2. And now it's just a simple equation for me to solve. 8x plus 6 is equal to 3x minus 6. I'm going to subtract 6 from both sides. I'm going to subtract 3x from both sides. And I get 5x is equal to negative 12. Divide by 5, and x is equal to negative 12 fifths. So it's okay to get that fraction as long as we make sure we simplify. All right, next one. We have a basis of 64 and 4. 64 can be turned into 4 to the third power raised to the x plus 1 power, and 4 to the 5x plus 2 power. So we got the same bases. Now we use our exponent rules. A power to a power means multiply those exponents. 3 times x plus 1 is equal to 5x plus 2. And now I just solve my equation. So I'm going to move my x's to the right. I'm going to move my constants to the left. And I get 1 is equal to 2x divided by 2. And 1/2 is equal to x. So make sure you're showing all the work you normally would as you're solving your equations. All right, last one. Here I have 25 and 3,125. So we can check and see, can 25 be turned into a 3,125? In this case, it can't. 25 squared is 625. 25 cubed is 15,625. So there's no way to turn a 25 into a 3125. So instead, can we make them both into something different? Well, they both have 5 in common. So 25 is 5 to the second power, and then it's still raised to the x plus 1. 3,125 is 5 to the fifth power, and then still raised to that 2x minus 6. So my bases are the same, so I'm going to focus on my exponents. Remember, a power raised to a power just means multiply. So 2 times x plus 1. Same thing here, 5 times 2x minus 6. And now I just simply solve my equation. So 2x plus 2 is equal to 10x minus 30. I'm going to move the 2x to the right-hand side. I'm going to add 30 to the left-hand side. And I get 32 is equal to 8x divided by 8, and I get x is equal to 4. So my keys are rewrite that base so that it's got the same base as the other side. So I might need to rewrite it with an exponent. Then I use my exponent rules to multiply my power by my power if necessary. And then I simply solve my multi-step equation if necessary. All right. Last little portion is our 2 little word problems. This one says the population P of a culture, so that's kind of like what's grown in a lab, maybe it's bacteria or something like that as they're testing something out, that begins with 40 bacteria and doubles every 8 hours can be modeled by this equation. P is equal to 40 times 2 to the t divided by 8 power, where t is the amount of time in hours. So we want to find t if p is equal to 20,480. So basically we want to plug that in place of p and then solve for t. So I'm going to put 20,480 in for p is equal to 40 times 2 to the t minus 8 power. Some of you might be tempted to multiply 40 times 2 right away, but remember, we can't do that because of that exponent. Exponents come before multiplication. But what I can do is they're multiplying by 40, so I can undo that by dividing by 40. So I divide by 40, and I get 512 is equal to t to the 2 to the t over 8 power. Well, I want the same base, so I need to rewrite 512. If you remember from an earlier problem, that was equal to 2 to the 9th. Okay. So I've got the same bases. Now I set the exponents equal to each other. So 9 is equal to t over 8. Well, t divided by 8, so I'm going to multiply by 8. And 72 is equal to t. So in 72 hours, it would have grown from 40 bacteria to 20,480. All right, next one says the velocity v in feet per second of a freely falling object that has fallen h feet, so h is the number of feet that it's fallen, can be represented by velocity is equal to 8 times h to the 1/2 power. Find the distance that an object has fallen if its velocity is 96 feet per second. All right, so I'm going to plug in 96 in place of v. So 96 is equal to 8 times h to the 1/2. They're multiplying by 8, so I'm going to divide by 8. And I get 12 is equal to h to the 1/2 power. Okay. So here's where we have to get a little creative. We want to get rid of that 1/2 power. So we just want to know what h is instead of the square root of h. So think of our exponent rules. We want to turn it into h to the first power. So what would I multiply times 1/2 to get it to a 1? Well, I'd multiply times its reciprocal of 2. So I have to put the same exponent on the other side. So I was multiplying by an exponent of 2 on one side. I made it an exponent of 2 on the other side. So 1/2 times 2 is just 1, or h. 12 to the second power is 144. So it would have fallen 144 feet during that 90, if it had a velocity of 96 feet per second.